Hi guys, thanks for coming out and for coming into the webinar. We're gonna go ahead and get started. Respect your time, so we'll as more folks come in. But we'll go ahead and get started. I'm Blaze Stewart. I am architect at Atmosera, and I'm a Microsoft Azure MVP. And I'm going to be talking about the Cosmos DB Graph API today. So hopefully to convince you why this is an awesome tool for doing a lot of different things that some people might not have thought about before. Maybe to give you some insight into how it works, or maybe just to kind of give you an idea of what you can do from a software perspective, and why that might be something that would choose this API over something else in Cosmos DB or another kind of database. So let's go ahead and get started with this. I just want to tell you a little bit about Atmosera first. I mean, we are consulting and consulting slash instruction training company slash MSP. So we do a lot of things in the Microsoft space. We typically focus on Microsoft stack, so that'd be Azure and all the Microsoft technologies, as well as development services in that space too. So apps on Azure would be one thing that we like to do. So if you're writing, React apps or JavaScript based front ends or whatever they might be, and you're hosting that on Azure, or if you're just hosting it on premise, we'll still work with that and .NET and all those kinds of things. We also will host your services if you so choose to work with us. We will have managed services where we will take care of the environments that you deploy to Azure. And if you want to get some training on any of the Microsoft technologies out there, we have definitely a lot of experience doing training in .NET, all things Azure, anything for development itself. That would be JavaScript front ends or back ends dealing with APIs and .NET code, JavaScript code, or databases, whatever that might be, Azure, SQL or on-premise SQL, and open source software as well. So that's kind of what we do. So enough about that. Let's just go ahead and dive right into the content, and we'll get started with that. So I want to start off by talking about what a graph database actually is. So this is going to be talking about it from the 40,000 foot view as the concept. So what this is. So most folks that are in development are going to be familiar with what a database is, I mean, at least somewhat. You if you've been around development or in the IT space, you kind of have an idea that a database in the traditional sense is a set of tables that you have data in, and you join those tables together using foreign keys, and you create your data structures in that, and that's what you use to store structured data, and that works well for a lot of use cases. And in more recent years, we've adopted paradigms like document databases like MongoDB or the SQL API inside of Cosmos DB. And these are storing data in a JSON format or a document format or an XML format that is more hierarchical in nature, and you can still query that and get data out of that, and folks are going to be more familiar with that. Well, there's a kind of a third kind of database that most people don't think about, and that's what we're going to be talking about today, and that's a graph database. And it's really pretty simple in its construction, but it's pretty profound in what it can do. So basically what a graph database does is it has a series of objects, and those objects can be anything. It can be a person, it can be a thing, it can be a place, it can be a company, it can be pretty much whatever you want. So we have a company here, Microsoft, we have Bob as a person, we have Jane as a person, we have Atlanta as a place, we have DC as a place, we have Office as a place, and we have things like a PC or an ISP as a business, or an ISP as a business. And all of these are objects, and they have properties associated with them. So Jane has a name, Jane has an age, Jane has whatever, Atlanta has geographic coordinates, population, an office will have something like an address, or whatever the properties that are unique to that are things that you can put in a graph database. So it's not just about having the objects in there. We have basically a set of keys and values that we can associate with any one of these objects that are kind of things that are going to identify the properties of these objects. And one of those would be some kind of unique identifier that would use as keys. And in a graph database, we call these nodes or vertices. Sometimes, depending on what literature you read, they are going to be called one or the other. In the context of the graph database inside of Cosmos DB, they're called vertices. And the vertices are basically what we think of as entities. I like to think of them as nouns. So these are the things that I'm going to be interested in. So once we have an idea of what the things are, we put those in as vertices, and then we express relationships between those. And that's what the graph turns into. And the relationships are identified by these lines, and we call those edges, or you might some others might call it some other name, but these are basically the relationships they have with one another. I like to think of these as verbs. So these are kind of the relationships that these entities will share with one another. So they have a verb that kind of identifies the relationship. So Jane lives in DC. Jane works in Atlanta. Bob works in Office One. Bob owns a PC. Microsoft services a PC. ISP provides internet to a PC. ISP1 interconnects with ISP2. So that kind of verbiage is the way that we think about edges and how they relate to how a vertice will relate to another vertice is through in these edges. And I like to think of that as a verb relationship. Now, typically these are expressed as one-way relationships. They can be two depending on the technology, but usually it's going from one vertice to another vertice by way of an edge. And when we look at the edge, when we go from one vertice to the other one, we're talking about a traversal. And that's what we typically call that. Is like if I start here on ISP2 and I do a traversal to Atlanta, then I do another traversal to Jane. Or if I start with Jane and I go the other way, I'm going from Jane to Atlanta. I'm traversing to Atlanta, then I'm traversing to ISP2. So that's called a traversal. And querying a graph database is typically done by way of starting at some kind of vertice. That's where I'm going to start. And then I'm going to traverse the graph to look for related vertices related vertices by way of the edges that are connected between them. So if I want to get information about relationships within the graph database, that's how I do it, is I traverse the edges that express relationships. And then by doing that, what I'm doing is I'm creating a context map as some kind of relationships between all of these different entities. Now, the power of this is really in how you can express a lot of those relationships without having to use a lot of statically typed relationships like you would typically have in something like an RDBMS. So with an RDBMS, you typically have to do that by way of keys, and the relationships have to be through joining tables and things like that make traversing any kind of data kind of arduous, because you have to do it by large abstract joins. Now, this makes that kind of traversing a little bit easier because it has the ability to directly to relate to any entity. There's no restriction on this vertice relating to any other vertice in the database. It can do that simply by just creating a new edge between one of these other vertices. And then that relationship is now established. And I can do that arbitrarily. There's nothing that says I have to go through another kind of entity to do that. So I don't need joining tables. I don't need foreign keys. I don't need any kind of external referent. I just need to establish that I have an edge between one vertice and the other, and that builds the relationship. And that's how I can maintain all these relationships between all these entities. And there is a lot of power in being able to express these kinds of relationships simply by being able to create all of these vertices between all these different edges between all these different vertices like we see here. So the graph database itself is a fairly straightforward concept, but it has a lot of profound use cases and things that make it more conducive for certain kinds of workloads that would be a little bit harder to maintain in something like more traditional database pattern like an RDBMS that's table driven or document database. So I want to walk through a couple of different use cases first, and then I'm going to do a demo. And then I want to close out by talking specifically about some tips and tricks that you can do to improve your performance on Cosmos DB. So that's kind of that's where I'm going to be going through the next, however long this lasts. So the first one I want to talk about is social networking. This is probably the most canonical use case for a graph database. Most folks, when they think about a graph database, they're probably going to be thinking, "Oh yeah, this makes sense. It's social networking." Yeah, and that's kind of true. I mean, social networking fundamentally uses this kind of traversing of entities to create a network of vertices or entities, whatever they are, and the relationships between them. And so this is what Facebook does. This is what Twitter does. This is what LinkedIn does. And if you have a lot of different kinds of entities that you want to relate together, you can create these kinds of traversals. So if I'm and the graph APIs that are available in things like Azure AD, or something like what you would have available on Facebook or in other entities, allow you to create these kind of traversals that do it on relationship lines between different kind of vertices in your graph database. So I can say that Bob patronizes coffee shop. Sue patronizes coffee shop. Or if I wanted to start at the coffee shop, I could say, who are the patrons of this coffee shop? And I could go, Bob and Sue are the patrons of the coffee shop. Or I could look for folks that have common interests. Maybe it's an author, and I want to look for all the common interest of this particular author, and that author has an interest in this coffee shop. So I could do that. I could get those relationships right here as well. Maybe it's something that was posted to social media, like Facebook. I could do who liked this video, who commented on this video, who is in this video. Those kinds of relationships you could have inside of a social network or a graph database that's supporting that. Or same with a photo. A photo is where was this photo taken? Who is in this photo? Who owns this photo? That kind of information would be stuff that would be associated in a graph that might be in a social networking setting. And so with this, you typically will have a lot of different kind of vertices: people, places, interests, events, photos, comments, all of these different kinds of entities that you're going to have as vertices in the graph database. And then the relationships between them, all the edges, would be like relationships between people. So and that person A is related to person B. The relationship is maybe they're siblings, or maybe it's parent, maybe it's a cousin, maybe it's something else, or maybe it's a check-in like Facebook does. A person checks into a place. I went to a coffee shop, so I checked into that coffee shop last week. Maybe it's an event that is, I'm going to an event. I checked into an event or something like that. So I'm interested in a particular topic. I'm interested in technology. I'm interested in writing. I'm interested in photography. And then, like you can tag people in photos. Person A or person B is in this photo. And so there's tons of ways you can build these edges. And this is just kind of the canonical use case. So if you kind of understand how that works in social media, you'll have a pretty good idea of how this works in other kinds of contexts as well. Social media is just probably the most common use case for it, but there's some that are more industry oriented. And I want to talk about a couple of these right now. So one of the common ways that folks use graph databases is in asset management. So traditionally, asset management is not that hard to do, but if you wanted to create an asset database using a graph database, you could think about it with a number of different kinds of assets. So assets come in all shapes, sizes, and forms. So if you can think about assets as a device, a phone, it could be a building, it could be networking equipment, it could be anything that you own that has something that you want to manage. And an asset management system allows me to create relationships not only between the people in this context, but also the things in this context. And so I can track the relationships between a device and a user, or a device and the network, or a device and the service of that device. And there's a lot of different ways that I can do that. So I can create, I say I have a PC. I can say Bob uses this PC. This PC is on network A or network B, and that's how I can show they have network credentials for this particular network segment, and that allows me to see that this device, a list of devices that are using network A, B, or C, and that's because they have the Wi-Fi credentials to log into that. Same with the phone. I could say that Jane uses a particular phone, or I could say that Jane uses a PC and it's using this operating system as I have an operating system that I support in my shop, and then all the PCs that use that are listed as one of those entities that I'm working with. So all of these different kinds of entities could be expressed as different things that I'm managing inside of an asset. So I could do this one way or another by simply creating a graph database that expresses all these different arbitrary relationships that would be more traditional, that would be more difficult to do in the context of a traditional database that would be something like an RDBMS. You could do it. It's not impossible, but it would be a little bit more difficult because you'd have to have a lot of different kinds of relationships that you're building and entities, and the table structure could get rather arbitrary. While this is just natively going to be able to do that without a lot of impedance to the data storage model that you're using. So this is one common use cases, and this might be what I have social, this should say asset management. I don't know, I copied the slide. This should say asset management, not social networking. You have people, places, assets, service tickets. Those would be the vertices. And this might be some of the use case, the edges that something is used by or located in or serviced by, or you might have a service ticket that's filed by or filed for a given device. So a device is person A filed a service ticket for device 1 or device 2, whatever it might be. You can express on those edges any number of relationships, something in that vein. So logistics would be another one. This is a very common one, and that's the one I'm going to do a demo on now. Not a full logistics application, but just to show you this. But logistics is a common use for graph databases as well, because logistics is a complex network of people and things and places that you kind of have to maintain all the different relationships between. So again, you will have things like shipments that you're trying to maintain. So this shipment is on truck A, and this shipment is going from warehouse B to warehouse C. The shipment is in city Y, or whatever it might be. And so Bob is flying plane A. Jane is managing this warehouse. This warehouse is located in this city. So you have all those different kinds of relationships inside of a graph database that are easily expressed using this kind of relationship like this. And you would have different kinds of entities like places, people, vehicles, containers, shipments. All of those are different kinds of things that you would put in as your vertices. And then you would create all of the, again, I copied and pasted to say logistic. I forgot to update that. You would update that, those edges through these kinds of relationships like this. So a vehicle is driven by person. The vehicle is located in city. A vehicle is traveling from city, or traveling to city, or traveling to, or a shipment is traveling to a place, or a container is traveling from a place. So all of that is part of the logistics management operation that goes into maintaining a logistics network, and those are very complex, and trying to figure out how I can efficiently manage all that and efficiently move resources around and get things from one place to another is a large part of what makes a logistics operation work in for things like supply chain management or manufacturing or warehouse management or retail or anything like that. Anytime you're moving stuff around on between a network of suppliers and consumers, or suppliers and manufacturers, or manufacturers and retailers and consumers, all of that requires the movement of goods from one place to another, or movement of raw materials from one place to another. And that's a complex network of people, places, vehicles, materials, whatever it might be. And you're trying to manage all that. And there's a lot of complexity that comes along with that a graph database, again, helps facilitate for that purpose. So again, logistics is one of the more canonical use cases outside of this. Now, a fourth one is a kind of an emerging one that is getting some traction on Microsoft, and and that's Internet of Things. And Internet of Things is, if you're not familiar with this concept, it's not a new concept. It's been around probably the better part of a decade now. It's connected devices. So as more and more devices are internet connected, managing those devices at scale is where things get more challenging the more devices that come all online. And these are typically not going to be co-located in a single building. They're going to be distributed globally or distributed regionally. They're probably going to be in places like that are not easily accessible, like factories or on container ships or in airplanes and any of that stuff that we're talking about with logistics. It's just stuff that is distributed all over the place, and you kind of have to manage all that at scale, at some way, shape, form, or fashion. And all these devices are not user devices. They're typically autonomous devices that have sensors on them that are collecting data. So geographic data, it's like they have GPS sensors on them, or they might have temperature sensors, might be a camera, it could be it might be barometers or accelerometers or impact sensors, whatever the sensor payload may be. It's got a bunch of different things. It's collecting data, and it's transmitting all that data back to the internet. And whatever that device is designed to do is basically taking a bunch of data and relaying it back to the internet, and is also receiving commands from the internet through a centralized management of all those devices. And so we end up having tons and tons of thousands, potentially millions of devices, depending on the context, distributed in a typically global setting. And you have to manage the relationship between all of those devices. And devices will typically not just be a single centralized device management system like a hub and spoke topology. Typically you have layers of devices, and all of those devices have different states and have different versions of operating systems, have different properties, different location information, and all that. Well, to model that, I can't, if I want to get information about that, I can't simply just go out and query all the devices in a given fleet of devices. Typically what we do instead of doing that is we typically we do what we call device twinning in the IoT space. And basically what that means is I have the same state data stored in the cloud as what is on the device. And I build a database where the state of all the devices is reflected in some kind of data storage mechanism. And to do that, I have a relationship set up with all the other devices. So I might have a bunch of devices that are deployed, and I use a graph database to reflect that. So I have devices that are connected to what we call edge devices, which are just basically kind of for collating messages and forwarding and filtering and a lot of other things that we do on the edge. And so all these devices have a complex network of devices connected to edges connected to other edges, and then the edge might report back to a centralized IoT management system like Azure IoT Hub or something like that. And all of this data is collected and maintained in a cloud environment so that I can go query this database to get information about the state of all the devices in my network. I can figure out when was the last time I can get a report of devices that haven't reported in a while, and I need to go, poke those devices to see if they are online, or maybe they see which ones have an outdated firmware that needs updated, or I need to do some kind of collection of data from a given geofence, and I want to say, go get me all the devices that have these lat long that fall into a given geofence, and I go out there, query that data from a graph database, and then pull that back into my application, and then I can go then send messages to all those devices without actually having to go out and query each one of those in the field, and then they will start sending me telemetry or whatever it might be within that thing, give that kind of geofence. So all of that is to say is that's one thing that I can do with the Internet of Things is reflect this. Azure actually has a product called Azure Digital Twin that implements something like this as a graph database. But you can, if you need to roll your own or do something like this, Azure Cosmos DB Graph API offers a way of doing this right out of the, and it's pretty straightforward and easy to set up. So again, that should say Internet of Things. I guess that's what happens when you copy and paste slides. Again, here's the things that you have. You have devices, edges, locations, and hubs. And it says you have things like managed by, reports to, located in. There's other different other kinds of relationships that you can have here as well. So these are some of the canonical use cases for this. Now that we've talked about a couple of the use cases for this, I want to talk about what is I'm going to show you a demo of how this works. And so we're going to get a little bit. We're going to go and do a technical. We're going to talk technology now, and so this is hopefully to give you familiarize you with the concept of a Cosmos graph database, what it might accomplish. But at the same time, I do want to show you one that actually works, and that's one I'm going to show you. I'm going to be using more of something that's in logistics for my demo. So this is a multi-part demo, so you'll have to bear with me on this. So let me get a browser window here, and let me pop this up here, and let me get the Azure portal pulled up right here. And the Azure portal will just give me a, I'm going to pull up my asset here. I already created the database because it does take a while for me to populate this with data. So I'm going to show you the code that I did use to populate it, but I just want to go ahead and bring this over here so you can see what I'm talking about. And I have this Cosmos database right here. And this is my graph, Cosmos instance right here. Let me make this a little bigger. And I can use Data Explorer to kind of poke around in this. And I have basically a graph database that uses airports as the vertices, and I use routes as the nodes. So there's a route between airports. So this one flies to this airport, and then this airport flies to this airport, flies from and to. So I have a graph database that basically represents vertices would being the airports, and the routes that are flown are the edges between those different airports. So this is kind of more of a logistics application for that. If I pull this up, if I load the graph, the Cosmos implementation of this gives me some it does give me the ability to kind of view this right here. It doesn't give me a lot of context, but I can definitely zoom in on any one of these and get an idea of what this is looking like. So this is, let me see if I can get a good example here. Let's see if there's an airport that's got more than one or two connections on it. So this one's got a few on here. This is an interesting relationship where you have, this airport is related to this one right here. So Anchorage, this is Alaska. So this has got St. Paul's Island, which is in Alaska, and then this one right here, which is Point Barrow, which is in Alaska. So this is an interesting airport right here where this one flies to this one and this one, and these are all related to one another. So there's edges between this one, and then you could go directly if we wanted to right here as well. So you have more than one kind of relationship right there in this particular entity right here. And this is how a graph database gets expressed in this context. Now this is Trenton Mercer. So this is in Trenton, New Jersey. So this is one that's got a little bit more complex relationship right here. And if I wanted to zoom in on this, I'm going to show you what this looks like on a map in a minute because I'm really apt to do that. But I can traverse this by simply clicking on the buttons here, and it'll try to create the relationships here and show me allow me to continue to expand on this. Showing this is kind of how this particular view of this works. So I can see that I have a little bit zoomed here. Let's go ahead and zoom out here so I can kind of see what's going on here. You can see all the edges as I traverse this are relating to one another and using a one-way relationship. As if I double click on these, it continues to expand outward. And that's a kind of a neat way to kind of explore your graph inside the context of Cosmos DB. So this is my graph that I have that I'm going to use for my demo app here in a minute. But you can see that it's using vertices and edges. And as I traverse this, you can see that it's going from one to the other. And so that is a visual representation of what you can do inside of Cosmos DB. Now, for my demo, because these are airports, it'd be a lot better to see this on a map. But before I get to that, I do want to show you some of the underlying technology that makes this work, and that is what languages this uses and what the engine behind this is called. So let me go back to my deck here for a second here, and the language that enables this to work is called Gremlin, and so Gremlin is the query language. Now, Gremlin is the query language. The engine is called Tinkerpop. I didn't come up with those names. I don't know who came up with those names. I'm not 100% sure why, but the Tinkerpop is the name of the engine that the Graph API uses, and Gremlin is the query language. If you or it's a graph traversal language, and it's a very expressive language that allows me to write queries that will allow me to kind of do what I was doing in the graphical representation of what we just saw inside the Graph API on Cosmos DB. So if I want to go from one node to another, I can use the Gremlin query language to kind of express that traversal. And I can filter using the Gremlin query language to kind of get an idea of outbound connections. I only want to get ones that with these criteria, and I can continue to traverse a graph with Gremlin just by simply tacking on new traversals and go arbitrarily deep if I need to get certain kinds of depth to my search criteria, whatever that might be. So what Cosmos does is it basically takes the Gremlin query language, and it is a protocol as well as a query language, and implements the Tinkerpop engine, and it basically inside of the Cosmos API, and then manages this for you so that you don't have to create a cluster. And so it's a wire level protocol of Gremlin on top of managed infrastructure, so that if you just use the standard libraries for Gremlin, then you don't have to, that the same libraries would work if you went and stood up your own implementation of Tinkerpop. Now, a lot of different companies implement this particular engine. Now, Neo4j does. Cosmos is one implementation of it. I think Neptune on AWS does. There's a couple other implementations of Tinkerpop and Gremlin, but Cosmos DB implements it as well. But not only do you get the benefits of Gremlin and Tinkerpop with Cosmos DB, you also get all the benefits of using Cosmos DB, which we'll talk about in a moment. And we'll talk about the specifics around Cosmos DB and how it relates to Gremlin and Tinkerpop. But I want to talk about these technologies right now. And this is the actual expressive. This is how you would express this. So like anything in Cosmos DB, you need a primary key and an ID to get this. So if you want to get a vertice, you need you need a partition key. Sorry, you can get any vertice by the partition key and an ID, and that just identifies everything inside of any unique record inside of Cosmos DB. So partitioning it doesn't go away with this particular implementation. We'll talk about that more in a minute. But if I want to get a given entity, I don't have to have the partition key. I can query it using something like this. You basically say, I traverse that looks like this. I can say, get me the graph.vertice v dash, and then I do has a partition key with the value, and then has a secondary filter of index property of value like this. And so I use these has filters to try to work on this. And there's other queries. There's other ways to traverse things if I want to do that as well. This is just looking at different ways to do querying inside of of Cosmos DB, and these efficiencies go from this way down. I'm going to talk about this a little bit more in a minute when I talk about tips and tricks for making this work better. But this is basically what I'm going to be doing in a minute. Is I'm basically going to be looking at everything in a single partition, trying to make everything work in that context so that I can have more efficient querying for this. So the Tinkerpop engine is going to take this query right here and interpret it, and it's going to then return a set of nodes or vertices really that I can then traverse, that I can then use in my application. I can display them, do whatever I want to with them. So let's go and look at a couple of examples of code that I might have for this. I have my first code that I wrote for this particular demo is a Node.js application. I have two different applications I want to show you. One is a Node.js application, and the other one is a .NET application. And they both use they both are using the Gremlin query language, and both are basically using the same database that we looked at. One of them I wrote as a script to populate the database, and I want to show you the how that works. And the other one, the .NET application, is an API that I wrote to use the database. So let's go ahead and look at this one right here. Let's look at the database population first. And this is basically taking some data that's airport data. This is online data that I've downloaded. It's CSV data. I'm looking at airports right here, and to show you what this kind of looks like. Oh, come on. This is just CSV data, comma separated file right here. I mean, just give this a more comment, take the word wrap off. And it's just a CSV file, and this is just all the airports in the world. I filtered this down to just filtered it down to airports in the United States for my purposes, which is fine. And so I'm not using all this data. And then I looked at this routes data, and this routes data is all the data between those airports. So basically the airline, the destination, and then the source and the destination, the starting point and the destination. So that's where I get the routes from. And this is literally thousands of records. I think globally there's over there's what 67,000 different commercial airline flights that exist as of when I downloaded this data. So that's what this is representing. I'm only using a subset of this. That's for data that is in the United States. So I'm not going to be traversing all this. So let's look at the code for this. What this looks like. Open up this index.js right here. This is Node.js right here. And this is kind of how this is all set up. It's pretty straightforward. In Cosmos DB, I just give it the endpoint. Like any database, I need to know what the server is, what's my username, what's my password, that kind of thing. Except for this one, I use basically the path for my my database as the user. And then the password is the key for the database. This is the path for the database. It's like I created a database called airport, and it's called what do they call it? A graph in the Cosmos DB, and then this is this is my graph right here, and so this is my database. This is my collection. If you're familiar with that nomenclature from the Graph API, I'm sorry, the SQL API. And that's what I use for the username and password. That's how Cosmos knows which one to use. And this is the password. I get that from the Cosmos. I can get that from the portal. And so I'm using the Gremlin client, which is just a Node.js package here. And then I'm using a package called FastCSV to parse that. So the way this works is basically, it's just, it's going down here. It's parsing, it's building some data sets in memory. And it's basically from those given CSV files. And this is where it's just building, in-memory copy of that data. And then this is where the actual data, this is the pertinent information right here that's kind of pertinent to what I'm talking about right here. So to kind of walk you through what this code does, it's basically using Gremlin right here. So I created two different Gremlin API, two different Gremlin queries and parameterized them. And so this one is using Gremlin. So I'm doing G, that's kind of, Gremlin dot add V, which is add vertice. I call it an airport for the label. Every vertice has a label, and then I have property, airport ID, and the airport ID is that property name, and then I've just got a string of properties that I'm adding to that, and that's how I add a new entity or new vertice into the database, and then the property, it gets injected right here. So the IATA code, the ICAO code, the lat long, and property lat long right here. And log lat long right there. So I know the geospatial coordinates of any of this data right here. So again, this is very straightforward. That's what that's doing. This one right here is it's creating the vertices. This one's creating the edges between the vertices. So the first thing I do before I go and create all these the vertices, which are the routes rather, I create all the vertices in the database. So I just basically seed the entire database with all the vertices I'm going to be working with, using a vertice add command. And so I'm taking all the airport data and just inserting that without any edges. And so that's what this first loop does down here. This loop right here is basically create vertice and create vertex, or it's creating all those vertices in this database. So it's basically going through a list of all of those airports that I created into an in-memory database, essentially, and creating populating it, and then it's creating an index. That's just basically some console to tell me the progress right here, and then I'm doing a client.execute, and this client.execute is basically just one at a time, adding each one of these vertices into the database. So once one finishes, I just go to the next, and it just does that over and over and over again. I did this in sequence. I could have done this in parallelization with this. I did this in sequence like this because when I tried to initially do this by just writing 50 or 60 to the database at a time, it was overwhelming the RUs that I had available in Cosmos DB. And so I was like, well, for my purposes, I can probably just do it one at a time and it won't overwhelm it, and it was fine. So once I add all the vertices in, I go in and I create all the edges. So this is basically going over those vertices again, and then it's creating edges between all those vertices. And that creates all those relationships that I was clicking through a moment ago. And so once that's, I'm definitely going to have a lot more of the edges in this case than I do vertices, because any one vertice can have a ton of different edges going out from it and then coming into it. So this one definitely has a lot of edges, and I'll show you that when I actually run the application. And so this one, when I run it, that's all it's doing is just seeding that database. And so again, a very straightforward example. I think I still have the results of it right here. This is where I ran it earlier today to populate the database. And again, nothing fancy. This is my output. I'm just showing progress. You can see it's serving airports served as 549 airports with 10,000 routes, essentially. So I have 549 vertices with 10,518 edges. And so I write the vertices right here. That's what this is doing. And that, of course, is only 500. And this one took a while longer to write. So it just, wrote all those. And then that's what I have for my output. And once I have that, I have a database. And that's what we saw already. I was clicking around on that right here. So it just basically seeded this database right here. And all of these different edges represent routes, to and from. And then I can traverse that with by clicking on any one of these routes and then double clicking on that to see what are the routes that I've got here. And again, it's just, that's what this data was seeded from, all that. So I want to pull the properties up. I can kind of see what that looks like. So what airport I'm looking at, Birmingham, Binghamton Airport, somewhere. I'm not even sure where that is, but you can see that by clicking through all this, I was able to get a few routes from that. So Again, kind of a neat way to see it. But let's look at this in another context. Let's look at a .NET app that has this the same data that, but this time I'm going to be reading it. So the second app that I have right here is just a simple .NET application, a little bit more involved, I guess. It's a client server app, a single page application where I wrote a controller. And I have a client for it. And this controller is using Gremlin queries to do something very similar to what I was looking at a second ago. Same data, same stuff I had a minute ago. I need to know my endpoint, my database, my collection. There's my key again. And I'm basically just creating a Gremlin client using the .NET SDK instead of this one, instead of the Node.js SDK. And this one is then just exposing a web API that receives some parameters. And then I can write a web app against this. So what I did here is just have a couple of gets, pass in some codes, and it gets me data back. And so this one is using Gremlin right here, but in this case, I'm using parameterized strings in .NET, getting data back, and returning it back to the client that ever calls it. And I'm using an HTML client to call this against this particular API right here. And so this calls it. Once I get this, it returns the whatever I'm getting back. And so this one just returns an airport. This one returns a list of all airports. This one is using a Gremlin query that says has label airport and has IAT code of whatever it might be, and that's just looking for a very specific airport. This one is looking for destinations from an airport, so I can say, what is my IATA code? I'm basically saying, go get me this airport, and then I'm doing an edge traversal right here, and where, and then I'm going out from that and getting the vertice that connects to that. Oops, I don't want to do that. I'm getting the vertice that it's connected to, and then I return those vertices back to the client. So it's just doing an edge traversal right here. This one is doing a little bit more than that. This one is looking for routes. So it's looking for direct point-to-point routes right here. It's a little bit more than a simple query like we have here. This one's basically start from an origin to a destination. It's going to repeat, basically doing a nested query inside of this. And then it's, this allows me to do some kind of like iteration. So if I want to like branch out, 1, 2, 3 iterations. I don't want to go more than 2 or 3 levels deep in a query within the context of Gremlin. That can get kind of slow if you have a lot of data. It can get rather large until I want to create a simple path until I have my destination, and then limit 1. Basically, just get me the first one that it finds in my list and return it. So it's just looking for a possible route between 2 different airports, and that's what this one does. So again, that's a more complex query right there, but it gets me it gets me a route and returns that back to the API. I don't think I have this one expressed, but if I run it, I should be able to get some data from it. So let's look at this. It's going to show me the output from this. This one is going to have the Swagger document because this is it's just a web API. I want to get some information. Let's look at this one, like this one right here. This is probably the more interesting one right here. That's going to do an origin and destination. Let's try it out. Let's see if it. So this is going to get this to work. ATL to CLT. Let's Atlanta to Charlotte, and execute. Now let's see if this can pull back some data. And it did. It pulled back. Here's a couple of different route options for me. This is the first one. This is just the first one it returned, and ATL to somewhere to this particular route right here to Charlotte. Okay. So there's a route there. Okay. If I want to go up here and get all the destinations, let's try this one out. If I want to get all of the outgoing destinations from Atlanta, I could just do that. This is going to return a ton because there's just a bucket of data. There's a ton of flights out of Atlanta. And that's probably why this one's going to take a while. Actually, this is probably not taking that long to load. It's probably the Swagger UI that's taking a while to load because that is it's returning back a lot of data. So let's go and look at the implementation of this in my front end here. Okay. let's exit the page and let's try this again, because Swagger is going to take a while to render all that because it's applying a lot of heavy lifting to that. And this is the same query that just returns all of the airports inside of the United States. And that's that first Swagger deployment that I did. I looked at right there. And if I click on any one of these, it's going to call that first API that I showed you, the one I just tried to run, that basically showed me all the outbound routes from it. So if I click on Atlanta, I should get a list of all of the routes from that. And so basically what I just did is I ran that Gremlin query and it returned me a list of all of the outbound routes from it. And so just using that, it's doing one node traversal outward from it, getting all of the connected vertices based on one outbound edge traversal from it. And so if I click on any one of these airports, you can see that I'm getting all the routes from it. And that's just using a Gremlin query to get this data. And so all these different airports have different outbound routes, and these paths right here represent the flight paths, I guess, and which are really just what's represented in the database as an edge. And that's what I'm representing here visually on a map using Google Map API. I'm just basically getting the lat long whenever pull back the airport list, dropping a pen on a map, and then I'm clicking on any one of these to get the vertice representing the vertices, but it's just using that traversal to determine what the outbound what the outbound from a given destination would be, and that is represented by an edge in my database. And so this is just a visual representation of that using more of a logistics application for that kind of data. So this gives you a lot of the kind of cool stuff that you could do with a Graph API. Now, I do have this code available online. In fact, I can show you that GitHub repo. If you want to download and play with this, I have this in a GitHub repo somewhere. Let me pull this GitHub repo up to show you where it is. And you can go out there, grab the same code and download and play with it if you want to for both projects. Graph API sample. If you want to grab this, it's at the one mule right here, the one mule / Graph API. So let's look at let's wrap this up with some questions and answers and just a few tips and tricks on this. This is just Cosmos specific stuff. So if tip one is to use a partitioning scheme that works for your data, just so you have performant queries. This applies to all Cosmos, but for Gremlin 2, I use a single partition for my data because it wasn't very large. So that's why my queries worked well. I'm using a single partition for all of my data. So I'm querying everything in that single partition. There's not multiple partitions. And so I basically use the country code as a partition scheme. And so all of my data is within that context. So it works well for my application. But if you had some other partition scheme, if I wanted to use every airport in the world, I would probably still use country. But if I wanted to traverse international flights, I would probably have a separate API for that. So to reduce the query overhead, I would have a partition key passed into my API, and then that would allow me to do a single partition query that would have more balanced partitions. But if I wanted to do international flights, I could have a separate query for that, and I just remove I could do cross partition queries, which are less efficient and they're more expensive. So just something to think about for your partition schemes. But think about how you're going to be using your data. You typically just want to optimize it for the lion's share of what you're going to be doing. Choose a partition key that's going to serve your data queries. That's going to be the majority of the time. In my case, within a country. So that makes sense for my data. So I just use the country code as the partition scheme in my data. 2 is understand the consistency models. I use eventual consistency for my default consistency model on Cosmos DB. For most of the other APIs, but including the Graph API, for most applications using Graph, that's probably enough. Eventual consistency basically means that if you update some data in the database, there's a small window of time where somebody could read stale data. And it also, if I do 2 writes that in quick succession, it is possible that the writes could happen. The latest write will be the ultimately be the one that gets replicated. It'll supersede all the other writes, but there is a small chance that somebody could read writes out of order. So if writes are, if ordering is important, then use consistent prefix if you need to guarantee that something's going to be read in order and things like that. Strong consistency means that you want all the replication to happen before you allow reads of that data. So any new data or any updated data will be replicated to all other nodes in the database before anybody can read that data. So it guarantees that all writes and all reads are consistent before any reads can happen against that. So this just prevents out of order data. This is not very performant. This is. So a lot of highly scalable databases will adopt eventual consistency. As a rule, I use it because most of my applications don't need strong consistency. Unless you demand it, default to eventual consistency, and it's probably going to be the best case for you. My third tip is related to that query that we just looked at. All those queries that we looked at is just use good query patterns. Again, try to execute your queries in a single partition. Avoid using unindexed queries, like conversion of case is a bad one. If you need to do a two-upper, you're not really running against indexed queries. Unindexed queries basically just kill your performance, and that's basically if you had to do like a two-upper, two-lower, case-insensitive searches, complex query. Anytime you're doing any kind of complex operation where that you have to do a conversion of data before you have to compare it to whatever it is that you're going to compare it to, that is an unindexed query. By default, everything in Cosmos DB, included the Graph API, is indexed. So if you're not doing any kind of data conversion before you do a comparison, it's going to be using index queries anyway. So you don't have to create any kind of special indexing on that. But if you have to do like a two-upper or two-lower or some kind of data conversion, you're not using indexed queries anymore, and you're going to have to read data off the store, and that's going to be very, very slow. So avoid that at all cost. So going back to kind of what that looks like, that's this slide right here. You want to be able to use within the context of a given partition, execute against the partition key and use the ID. Also, across partition scans, this is okay. It's probably fine to do. If you want to do, like I said, in my context, if I'm using Contri, I would probably, my cross-partition scans would basically be international flights. And that works for my context, for my application. Otherwise, I'm going to use domestic flights for all my queries, and that's fine, and so on. And that's what you get. So you just basically want to don't use unindexed searches, because that's just bad. Avoid these at all costs if you can. Some workarounds would be just to store the data in a case-insensitive form, or if you need to do some kind of data conversion, do the data conversion and store the data conversion in that way so that you can index that converted data as part of a given object. So those are just my tips and tricks for Cosmos, but they apply to Cosmos DB as Graph API as much as they do the SQL API, Mongo API, or the Table API, whichever one that you choose. So I do want to leave some time for questions. We do have a few minutes left. I don't have a question slide here, but if you want to pose slides, if you want to pose question, there's a comment question feature that you can add again here. So the first question is, does relationships between Node.js have to be one way? Do they have to be one way? In Cosmos DB, they are one way. The Graph API supports one way, but if you need to represent a two-way, just add two vertices. That's easy to do. And so that the relationships expressed in Gremlin have to be, they're one way relationship. Other implementations of graph databases don't. They allow for two-way, but in Graph API, if you need a two-way, just add two vertices, add two edges, and that's that. That way you're doing outbound. You can query on inbound edges, so if you need to, you can do that. So I can say, get me all the inbound edges from another vertice. So you can query against inbound and outbound edges. So if you want to have two-way relationships, you can, but the database only supports one way, but you can query against inbound vertices inbound edges and outbound edges. So that is one way to get around that if you want to. So both are supported in Gremlin. I don't think I showed that, but you do have that ability. So can you explain to me tip 2 again? Let me, what was tip 2? Tip 2 was, this is some data I was doing on Cassandra. Tip 2, consistency. Okay. Tip 2 was understanding consistency in Cosmos DB. Okay. In Cosmos DB, you have this tension, or any database really, between what we call strong consistency and eventual consistency. And there's different implementations of that in Cosmos DB. So strong consistency basically means that when I do data writes, before that data can be read, it will be written to every possible data point in the database. So in other words, if I have 10 nodes, I'm going to replicate that data to all 10 nodes before it can be read. And it means that nobody can read that data until the data has been replicated to all available nodes. That's what strong consistency basically implies, is that any inserts or any updates to data will be written to all available nodes before it can be read. Eventual consistency means that the data, that it doesn't guarantee that the data will be readable before the replication is complete. So eventually it will be completed. But basically what that means is if I do an update, for instance, if I do an update on data on one node, then what's going to happen is there's going to be a potential read on another node against old data. So if I update a record on one node, it takes time to replicate that to the second node. It is possible that somebody could query that second node and read old data before the replication happens to update that record. And that's why, and so within that window of time, there's no guarantee that somebody that's reading that data is going to read the latest copy of that data. Eventually, it will be the latest copy of that data. That's why we say it's eventual consistency, but there's no guarantee that it will be the latest data when I read it. That window of time usually in eventual consistency databases is very small. And so that basically implies that while it's possible, it's not probably going to be a problem for most cases. Databases that enforce strong consistency usually don't scale well. It's because of that replication problem that has to happen. And so I can't scale this to hundreds of nodes and create an experience that I have data writes that are going to be able to be read immediately. And because I have all of this replication that has to happen, that's very slow if you have a lot of data nodes. And so typically things like SQL Server don't scale up to dozens and dozens of nodes because of that. Eventual consistency, because I don't need to have the replication happen, means that eventual consistency works for databases that scale horizontally. I can have hundreds of nodes on them or dozens of nodes on them without having to worry about all this write replication to happen. And so this scales better. This guarantees consistency better. So it's a trade-off between the two. So this one, if I need throughput and low latency, I will go with eventual consistency. For most of the time, this one is the one I'm going to be using because my application doesn't demand it. But if I need that strong consistency, that's the one I have right here. So hopefully that helps you understand a little bit better what I'm talking about there. Question is can you, next question is, can you tell us about comparing the Neo4j and the Cosmos Graph API, Graph databases? The performance differences, if NeoDB is better than the Cosmos Gremlin, etc. It's not apples to apples. So, okay, Neo4j is an implementation of a graph database. And Neo4j basically they implement Gremlin as well. Is it the performance differences depend on a lot on what I've just been talking about, and that's the consistency model that you adopt in Cosmos DB, as well as the complexity of your queries and what you're really trying to go for in that context. So Graph API on Cosmos DB with eventual consistency will be with a single partition or a well partitioned database will rock. It'll be a rocket. It'll work well. I don't think that I don't think you're going to have any problem scaling that at all. And Neo4j it's similar in that respect. I don't think it's going to have any problem scaling. It's just the biggest difference between the two is that Cosmos DB implementation of it allows you to change the consistency model within the graph database. And I don't think Neo4j supports strong consistency, while it only supports an eventual consistency model, while Cosmos DB can support these other ones. So if I go with one of these down here, it'll penalize you on performance. But if you go with eventual consistency on Cosmos DB, you can have great performance in that regard. And the other thing that Cosmos DB gives you is a fully managed database. It's database as a service, so I don't have to create maintain any kind of infrastructure for this. As far as I understand, with Neo4j, you can install that on premise, or you can do their cloud version for you, what have you as well. So there's that potential as well. I don't think that you're going to have any issue using Cosmos database for performance as well. Just a lot of it depends on partitioning schemes and your queries and how they're going to be taking advantage of partitionings, as well as the consistency model that you adopt. Eventual consistency in a single partition, that's fast. That's going to work well every time. If you're using one of these, a strong consistency model where you're doing cross partitions queries or non-index queries, it's going to slow. So that's really what makes this perform well, or does it perform well. I heard that database Cosmos DB can be a document database and an RDBMS as well. If no, how is that possible? Can Cosmos DB be? Yeah, sure. It's Cosmos DB has multiple paradigms. Cosmos DB supports document databases. It's got a protocol implementation of Mongo. It's got a protocol implementation of Cassandra. It's got a protocol implementation of Gremlin. It's also got the proprietary implementation of a SQL of a document database called the Core API or the SQL API. It's kind of confusing, even though it's a NoSQL database. And it supports a table database that's proprietary to Microsoft as well. So it supports 5 different paradigms. All of them have this same consistency stuff that I've been talking about here that you can tune and so on. But they're different implementations of different database paradigms. So yes, you can support. It's not an RDBMS in the sense that it is a RDBMS like SQL Server. It doesn't support foreign keys. It doesn't support all that kind of stuff that you come to expect with something like a SQL Server database. So I wouldn't call it an RDBMS in the traditional sense. It is a remote database management system, but it's not an RDBMS in the sense of a SQL Server database where you have tables with foreign keys and relationships and strong schemas and all that kind of stuff. So it's a different kind of database. When used appropriately, it's a great database. When used poorly, it's a terrible database. It's just making sure that what you're using it for maps onto onto what you're going to be using it for. So I wouldn't recommend investigate it, use it, learn about it, figure it out, learn what its strengths and weaknesses are, then adopt the paradigm that best fits your application's needs. I've talked about some of the applications that Cosmos DB Graph API is useful for, that it really does well with, and the API that like I said, for logistics, it's a great use case for that, IoT, so et cetera. So there's a lot of things that you can do in that case. So hopefully that answers that question. So I think we've gone a little over. Thank you guys for hanging in there. These have been some great questions. Hopefully this has been informative, and you guys will have we'll be posting this webinar on our YouTube channel so that you can get a recording of it if you so choose to review this. The source code is available, and I'll put that on the YouTube channel recording as well, so you can get that. If you wanted to play with my little demo here, it's pretty easy to run. And I encourage you to explore this and just learn about it. And hopefully we'll see you again next time on a Winterlight webinar, Atmosera webinar, and we will be posting this one again shortly. And thanks for coming out. I hope to see you in the future.